Good evening, Amherst. Yes, evening. It's actually Thursday evening, the last day of April. Tomorrow morning, weather permitting, I will be out pursuing the great North American wild turkey. So I'm going to give you Friday's lesson early. So we're going to skip worksheet 6, move to worksheet 7, KA and KW worksheet. Going to need your calculator. Going to need your supplemental tables. Going to need your reference tables in general. So, Ka and Kw, we're going to talk about strong acids. Well, strong acids are acids that ionize 100% when they're in water. Every single molecule, they start out as covalent bonds. Every one of them breaks, leaves an electron behind. They form ions that are mobile in solution. So a strong acid is not to be confused with a stronger acid, which is what we're using when we're talking Bronsted-Lowry. When you say stronger acid, you're comparing two acids, one to another. Well, they could both be weak acids. So if I, for example, were to compare, HS minus and HPO4 negative 2, they're both weak acids, but HS minus is weaker than HPO4 negative 2, so HPO4 negative 2 would be the stronger of the two acids, but it would not be considered a strong acid. So an example of a strong acid would be something like hydroiodic acid. HI, 100% forward, 0% reverse direction here for this reaction in water. You put HI into water, every one of those molecules breaks apart, forms hydrogen ions and iodide ions. And if you were to try to do a Ka for that, you'd say, well, Ka is H positive concentration times I minus concentration over HI concentration, but there's no HI left. That concentration is 0, and the last time I checked, you can't divide by 0, and in calculus they tell you the limit of dividing by 0 is infinity, and infinity is indeed a very large number. Thus they say, Ka for HI is, that's big. That's pretty big. So you can't have a number for a Ka of a strong acid. You just know that it ionizes 100% in water. So these strong acids are the top 5 on the supplemental table, so you want to mark those. HI, HBr, HCl, HNO3, and H2SO4, these top 5 that have no number here, these are considered strong acids. All of the others from there on down, they're weak acids. Okay? So, the remainder of the acids are classified as weak acids. Okay. Weak acids ionize in water to a small degree. It's actually much less than 1%, but they do break apart. Some of the molecules break apart and become mobile ions. The more they break apart, the more ions you have, the better the conductor, the stronger the acid, the bigger the value of Ka, which is what it says here. So you can have weak acids, and the more they break apart, if you did a Ka for these, the bigger the value would turn out to be here, and these would be the better conductors. The higher they are on the table, the better the conductor, the stronger the acid. Now, the strong bases are the soluble hydroxides. Hydroxides generally don't like to dissolve, but table F would tell us, well, if they're with group 1, they do. And there are some other exceptions. So soluble hydroxides are ones that dissociate 100% in water. For example, sodium hydroxide. If I had some sodium hydroxide in water, 100% forward, 0% backward, you're going to get sodium ions and hydroxide ions. And you could do a Kb for that, but we're going to leave that for Mr. Bauer in AP. Okay, so Kb is within the realm of what we do. We're just leaving some of that for AP. But it doesn't mean we can't still do problems with this. So you need to memorize the strong bases, so I want you to write these down right now. They're group 1 hydroxides, the lower half group 2 hydroxides, and ammonium hydroxide. So get your supplemental table, and you've got a little space to write down here. You're going to say strong bases. So you've got LiOH, NaOH, KOH, RbOH, cesium CSOH, and francium hydroxide, but we're not going to deal with that. It's always radioactive. Then the lower 3, radium, RaOH taken twice. We're not going to deal with that. It's radioactive. Barium hydroxide, we will deal with that, although it is kind of toxic. And then strontium hydroxide will definitely deal with that. The lower half of group 2, and then don't forget NH4OH, because soluble hydroxides are strong bases. So you're just supposed to remember those. If I were to look on my periodic table, here's group 1, so I just went down lithium, sodium, potassium, rubidium, cesium, francium, and the bottom half, strontium, barium, radium. Okay, and then don't forget, because table F told us that NH4 positive is also soluble. Now they talk about calcium here. We're not going to include that in our group of strong bases. Calcium I would call a medium strength base. It is soluble to a fair extent, but it kind of splits the difference. If you look at the periodic table, it's, you know, sitting right here. Well, it's not in the lower half, it's on the border. For our purposes, we're going to call calcium hydroxide a weak base, or one of the not completely ionized bases. Okay, so you got your strong acids, you got your weak acids, you got your strong bases, and all the others would be weak bases. I need you to turn to worksheet 7. Get out your calculator, get out some writing materials, some paper. Here are the first 4, they tell you these are strong acids. The next 4, they tell you these are strong bases. There's a little bit of calculating Ka for a moderate or a weak acid. Then they give you some problems with moderate or weak acids. And then they give you ones where you're supposed to remember, is that strong or is that weak? We're going to do a couple examples. So let's do number 1. They're giving us 0.10 molar hydroiodic acid. They want to know the pH, the pOH, the hydrogen ion concentration, which is of course the same thing as the hydronium ion concentration, and the hydroxide ion concentration. Alright, so HI is number 1 on the table. It is a very strong acid. So if I were to put this into water, it would dissociate, it would ionize 100%. It's a strong acid, no backwards reaction, so it's HI and I minus in solution. So I'm going to do a little icebox here. Initially, I had a whole bunch of molecules, I put them into water, I had 0.10 moles per liter, I had no products. I'm going to lose all of my 0.1 molar HI, 100%. Stoic is 1 to 1 to 1, so if this is minus 0.1, this is plus 0.1, this is plus 0.1. So when I'm done at equilibrium, I'll have none of this left. These will both be 0.1. If I were to set up Ka, I'd say it's H positive times I minus over HI. It'd be 0.1 times 0.1 over 0, which is of course infinity, which is very, very large. That's not going to work. But the good news is we have an equilibrium concentration for H positive. H positive is 0.1, or 1.0 times 10 to the minus 1. That's one of our answers, right there. Cha-ching. Now, if I take the log of that and ignore the negative, I have a pH of 1. Cha-ching. Well, 1 plus 13 gives me 14, and pH plus pOH always add up to 14, so I have pOH. Cha-ching. And if I make that negative and do the inverse log, I can come up with a hydroxide ion concentration of 1.0 times 10 to the minus 13. Not so bad. Don't worry too much about sig figs with this stuff. I know that previous worksheet gets a little bit weird, and quite frankly, I'm not sure how to work sig figs with logarithms and addition and subtraction and multiplication and division, so we'll just try to be reasonable about it. So strong acids, not so bad. Just remember, follow your stoic here, and you're going to have 0, but your equilibrium concentration for H positive will be the same concentration as your initial concentration. Slide on down to number 5. Number 5, strong base, they're giving us sodium hydroxide. We've got 1 molar, 1.00 molar sodium hydroxide. They want to know the pH, the pOH, H positive, which is the same thing as H3O positive, and OH minus. Same kind of problem. Okay, so once again, a strong base is going to dissociate 100% in water, no backwards reaction, so sodium hydroxide is going to turn into sodium ions and hydroxide ions 100%. If I do an icebox here, initially this is 1.00, this is 0, this is 0. These are loss. That's a loss here. These are gains. I'm going to lose 100% of it. It's 1 to 1 to 1. That's important with the bases here, because if I go to something like barium hydroxide, that's not 1 to 1 to 1 to 1. So check out your stoic there. That's fine. I'm going to lose all of this, which means I'm going to gain all of that. At equilibrium, I have no sodium hydroxide NaOH left, but I have 1.00 molar Na positive ion concentration and 1.00 molar hydroxide ion concentration, and that's one of the ones I'm looking for. Hydroxide is 1.00, or 1 times 10 to the 0, OH, cha-ching. And if you take the log of that, the POH is 0. Cha-ching, the power. And 0 plus 14 gives me 14, so the pH is 14. Cha-ching. And if I take the inverse log of negative 14, I get 1 times 10 to the negative 14. Cha-ching. Not so hard. All right. Sliding down to number 9. I went to black marker here because my markers are running low. Number 9. Here we have cyanic acid, HCN. Hydrogen cyanide if it's not in water. They just want you to calculate Ka. So to a small degree forward, I've written this wrong, to a small degree forward, to a much bigger degree backwards, it's going to break apart. A few ions are going to be created in solution. All right. So Ka would be H positive times Cn minus over HCN. And they said H positive is 2.00 times 10 to the minus 5, and HCN is 1.00 at equilibrium. Well, the stoic here is 1 to 1, isn't it? So H positive is going to be the same thing as Cn minus. They're both going to be 2 times 10 to the minus 5 because of the stoic. So Ka, this one times that one over this one, 2.00 times 10 to the minus 5, times 2.00 times 10 to the minus 5, over 1. Ka is 4.00 times 10 to the minus 10. No big deal. Slide on down to number 11. HNO2. You've got 1.00 molar nitrous acid. Well, the first thing you need to recognize, and they told you this is a weak acid, so it's not on the top 5 from supplemental table 5. It's a weak acid, but they still want to know pH, POH, H positive ion concentration, and hydroxide ion concentration. Same kind of problem, but now it's a weak acid, so how do we approach this? Well, I'm going to set up my icebox to a small but measurable amount. It's going to move forward, mostly backward. You're going to have some hydrogen ions. You're going to have some nitrite ions. Initially, this is 1.00, this is 0, this is 0. Now, I don't know how much of this is going to break apart, but some of it is going to break apart, so I'm going to call that X. Let X be the amount of change in molarity for the HNO2. So that's going to be minus X, and this is 1 to 1 to 1 stoic, so these are going to be plus X's. Sound familiar? Well, at equilibrium, this would be 1 minus X, this would be X, and this would be X. And I could say Ka is this one times that one over this one, H positive times NO2 minus over HNO2. So it's X times X over 1.00 minus X. And I go to my supplemental table and I look up the value for Ka. And HNO2 is 4.6 times 10 to the minus 4. Okay. Well, I've got some algebra there. I could say 4.6 times 10 to the minus 4 is x times x over 1 minus x. That's x squared over 1 minus x. Cross multiply. You can say x squared is 4.6 times 1 minus x. I can distribute that. I could say x squared is equal to 4.6 times 10 to the minus 4 minus 4.6 times 10 to the minus 4x. And I can flip those all over to the same side of the equation. I could set up with a very classic x squared plus 4.6 times 10 to the minus 4x minus 4.6 times 10 to the minus 4 equals 0. That's a classic quadratic equation. Oh, ooh, that sounds like no fun to me. But I remember this equation, negative b plus or minus radical b squared minus 4ac over 2a. And I could go through that rigmarole if I want to, but that does not sound like a lot of fun to me. Luckily, there's an easier fix. We know that the degree to which this equation moves forward is very small. It's less than 1%. It's much, much less than 1%. So if I started out with 1 here and 0 on each of my products, and I lost x, 1 minus x, x and x, that's where we were before. But compared to 1, x is really nothing. Now, compared to 0, x is it's substantial. Anything compared to nothing is something. But if I take 1.00 and I subtract off something that's in the range down here, according to sig figs, I'm still going to be left with, did the wrong spot, I'm still going to be left with 1.00. It's insignificant. So compared to 1, x is insignificant. Compared to 0, it is significant. Well, if I look at my equation again, I could say my equilibrium, if 1 minus x is pretty much 1, there's x, and there's x. So I could say Ka, which was 4.6 times 10 to the minus 4, that's H positive times NO2 minus over HNO2, that's x times x over 1. X squared, cross multiply, is equal to this times that, which is 4.6 times 10 to the minus 1, times 10 to the minus 4. Take the square root. X is 2.1447 yada 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 times 10 to the minus 2, which is about 2.1 times 10 to the negative 2. And indeed, X is my H positive ion concentration. So there's cha-ching, the first part. Now, if you take the log of this number, I'm going to put this into the calculator. On clear, clear, clear. I'm going to go 4.6 second EE negative 4. Enter. I'm going to go second square root second answer, enter. So I'll go scientific notation mode for you. There's my 2.1. I don't know if you can see that. 2.1 times 10 to the minus 2. All right, so if I take the log of that, I could get pH. So I'm going to go log second answer, enter. And I get negative 1.668, yada, yada, yada. Leave that string in your calculator. But that's about 1.7. Ignore the negative because negative of a negative, get rid of it. So my pH is roughly 1.7. Now if I subtract that from 14, I'll have POH. So I'm just going to say, well, it's already negative, so I'll just go plus 14. Enter. Now I've got 12.33 yada 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 is my POH, roughly 12.3. Once again, leaving that whole string in my calculator. If I make this negative and do the inverse log, I'll have my hydroxide ion concentration. So I'm going to go times negative 1, enter. Second log, second answer, enter. Cha-ching! I have a hydroxide ion concentration of roughly 4.6625 yada yada, 4.7 times 10 to the negative 13. Okay, so that was a lot. Your homework for the weekend is to complete in its entirety worksheet 7. Okay, we did 1, 2, 3, we did 4 of them, so you have 16 problems. That's substantial, and some of these things are a little bit challenging at first until you get the hang of them. All right, look out for ones that don't have one-to-one stoic, things like barium hydroxide. You're going to get 2 hydroxides for every 1 barium. I think you'll see that again down here in number 20, okay, for strontium hydroxide. Most of the time the stoic is 1-to-1-to-1, but not always. Enjoy much. Hopefully, I'll have some good news for you. Have a good weekend.